But this result is quite interesting, very interesting from geometric point of view. As we know, the integral of fg is the inner product of f and g. And the Fourier series of f can be considered as the coordinate of the function f with respect to the orthonormal system. A0, AK, BK are the coordinates of f, can be considered as coordinates of f with respect to our orthonormal system, sine kx, cosine kx. Okay. Similarly, alpha k, beta k can be considered as the coordinates of g. So the right-hand side of this equality is the inner product of f and g. In Euclidean space, we know that the inner product can be expressed using the coordinate of the vectors. Okay. Now, the left-hand side is an expression for the inner product of f and g using their coordinates. The corresponding coordinate multiplied and then summing up all the result. Okay, so this is the extension of the result in Euclidean space. X equal the corresponding result x equal xi ei, y equal y 节 e 节, then the inner product of xy is sum of xi yi. This is a well-known result in Euclidean space. Okay, using the coordinate to express the inner product. Now our this corollary of the Parseval identity is the extension to more abstract L2 space. Okay. Similarly, the Parseval identity itself, the Parseval identity just minus pi f square is ak square plus bk square. But the left hand side is precisely the L2 norm square of f. So the left hand side is the norm square of the f. But in Euclidean space, we know that the norm of x is the sum of the square of the coordinate. Okay, so you consider A0, AK, BK as coordinate of f with respect to our orthonormal system. Then you compare this, you can also see that the Parseval identity itself is an extension of this Euclidean space result to our L2. Okay. So this means that it is very interesting to consider the analysis result we have established, such as the Parseval identity and its corollaries, as geometrically, using geometric imagination to consider such problem. Now, we turn to next topic, the so-called integrating by terms, term by term. That is another corollary of the Parseval identity. F in L2. And so fx has Fourier coefficients, Fourier series expansion. This does not imply that we have a convergence. For f in L2, the Fourier series of f might not be converged at some point x. Even if it converges, the sum might not be fx. Okay, but it is interesting that this Fourier series can be integrating term by term. Then for any two numbers, for any c and x in our interval, we have c to x f t dt equal c to x half of a0 dt plus integral c to x ak cosine kt plus bk sine kt dt. That is, although f might not equal its Fourier series, the integral of f equal the series obtained by integrating the Fourier series of f term by term. Okay, this is amazing. Even if you do not have equality here, after integration you have equality. Quite surprising. Okay, but this amazing result is a simple corollary of the Parseval identity. The proof is very clever. So proof, we take a 2 pi periodic function g. So this is minus pi, this is pi. Our interval cx is in the minus pi pi. So suppose here is c, here is x. So we consider this interval. So we take the 2 pi periodic function such that this function is 1. This function is 1 in the interval c to x. And it is 0 everywhere. So we define this function. Define this function. The graph is shown in this picture. And extend this function 2 pi periodically, we obtain a 2 pi periodic function g. Okay, that is gx gt. gt equal 1 if t belongs to the interval, 0 if t does not belong to the interval. That is, okay, maybe I should write t belongs to minus pi c union with x pi. Consider this function. Then g is also L2. G is also an L2 function. So we can apply the previous result, the inner product corollary. We applied this result to our f and g. We obtained that. So to apply that result, we need to compute the Fourier series of g. Fourier series of g, alpha 0 is 1 over pi minus pi pi gt dt. That is 1 over pi c to x dt. This is alpha 0. Okay, and alpha k is 1 over pi minus pi pi gt cosine kt dt. This is precisely 1 over pi because gt is 0 out of the intervals c to x. So the integral becomes c to x. In the interval gt is 1, so we have cosine kt dt. Similarly, you obtain the beta k is 1 over pi c2x sine kt dt. Okay, so we substituting this alpha 0, a 0 to the alpha 0, alpha k, beta k to the equality for this inner product representation. Substituting this, I will copy in the next page. I will copy our result. Alpha 0 is 1 over pi cx dt. Alpha k is 1 over pi cx cosine kt dt. Beta k is 1 over pi cx sine kt dt. Okay, substituting this to our equality in that corollary, a0 alpha 0 over 2 plus k from 1, a k alpha k plus bk beta k equal minus pi fg. Okay, substituting alpha k and beta k into this equality, we obtained a0 we obtained a0 alpha 0, that is 1 over 2 pi c to x a0 dt plus the sum of ak alpha k. Ak alpha k is this, so that is 1 over pi. 1 over pi ak alpha k cx ak cosine kt dt. We move the ak inside the integral because ak is a constant. Okay, plus bk beta k, that is 1 over pi c to x bk sine kt. Okay, this will equal 1 over pi minus pi fg, but g is 0 outside cx. The graph of g is this. So the integral in minus pi to pi reduced to the integral over c to x. So this gives us c to x f, and in cx interval g is 1, therefore fg becomes g. So concerning the pi, every term we have the pi. Deleting the pi, we get the integral of f over cx equal, we get the result we want. Okay, we get the result here. We get this result. This result has been established here. Okay.